Let us have some example problems concerning electric flux. In our first problem, it says that a uniform electric field with 9,000 newtons per coulomb is parallel to a flat surface area of 25 square meters. Calculate the electric flux passing through the square region. In this problem, the area of the square and the uniform electric field of the area are given. We can also note that the electric field and the surface area are parallel with each other, and therefore, the angle of orientation is 0. From our working equation phi sub E is equal to E times A, we can easily substitute the given and solve for the answer. And the final answer we are looking for is 2.25 times 10 raised to 6 Newton meter square over coulomb. Quite easy, right? Let us have a more challenging problem. Identify the electric flux passing through a rectangle with sides of 13 meters and 25 meters found in a region with a uniform electric field of 200 newtons per coulomb and an angle of 55 degrees with respect to the horizontal. In this problem, the length and width of the rectangle, the uniform electric field of the area, and the angle are given. Do you think you can solve it? Okay, let us check if we got the same answer. The area of a rectangle can be calculated using length times width. The length is 25 meters and the width is 13 meters. Multiplying these two, the total area is 325 square meters. We can use this area in finding the electric flux by substituting this in our formula, E times A times cosine theta. Let us substitute the values. 200 newtons per coulomb times 325 meters square times cosine 55. Finding the product of these three, the electric flux passing through the rectangular region is 3.73 times 10 raised to 4 newtons meter square over coulomb. Try to solve this last problem. A disc which has a radius of 0.10 meter is tilted at an angle of 30 degrees to a uniform electric field E with a magnitude of 2.0 times 10 cube newtons per coulomb. You are asked to calculate letter A, the electric flux through the disc. Letter B, the flux through the disc is turned so that its normal is perpendicular to E. And letter C, the flux through the disc, if its normal is parallel to E. I will post this video and I will give you time to solve for the required values. Okay, let us check if we have the same answer. The given in the problem are the radius, the angle, and the electric field. For letter A, we are asked to calculate the electric flux, and we cannot do it until we have identified the surface area of the disc, which we can identify using the formula A is equal to phi times r squared. Substitute the values. The area of the disc is 0.0314 square meter. Now that the variables in finding flux are all given, we can substitute these in our equation. EA cosine theta, which is equal to 2 times 10 raised to 3 newtons per coulomb times 0.0314 square meter times cosine 30 degrees. Solving these, our final answer will be 54 newtons meter square over coulomb. For letter B, it asks for the flux if the angle is turned perpendicular. Therefore, the angle becomes 90 degrees. Since cosine 90 degrees is 0, therefore the electric flux is also 0. For the last item, we are asked to find the value of the flux if its normal is parallel to E. We say that the angle is 0 for parallel orientation. Substitute this with the given in the problem, 2.0 times 10 cube newtons per coulomb times 0.0314 square meter times cosine 0, and performing the operation, the final answer would be 63 Newton meter square over coulomb. And that, class, is how to compute electric flux. For your assignment problem, Pause this video and take a screenshot of this problem and try to solve it. The solution will be discussed during your next sync session. In the next video, we will talk about the scientific law that establishes the mathematical relationship among charges, electric field, and electric flux, or the Gauss's law. But that is all for this lecture. I am Gilmar De Castro, and see you in the next video.